Okay, let's talk about quantum computing. I mean, there's so much hype out there, right? It's genuinely confusing to figure out what's real and what's just noise. So in this explainer, we're going to dive in and clear up the single biggest misconception that fuels pretty much all of that hype. This whole idea of a direct competition. I mean, you've seen headlines like this all the time, right? They're always framing it as some kind of epic showdown, a performance contest, where one technology is going to make the other totally obsolete. And that right there, that's the real question we need to be asking. Because, framing it as a simple competition, it just completely misses the point of what these incredible machines are, and maybe even more importantly, what they're actually built to do. All right, so let's just tackle this replacement myth head on. This idea that your laptop or your phone will one day be a quantum computer, it's not just unlikely, it's a total misunderstanding of what these things are even for. So here's the absolute core of it all. Quantum and classical computers, they aren't just different in terms of speed or power. They are built on entirely different physical principles. We're talking about two fundamentally different models of computation, designed to solve completely different kinds of problems. And to really, really get this, we've got to go right down to the most basic level, the fundamental building block. We're talking about how each machine represents a single piece of information. And it all starts with the huge difference between a bit and a qubit. Okay, so look on one side, you've got the good old classical bit. Think of it like a light switch. It's simple, it's reliable, it's either off, a 0, or it's on, a 1. That's it. End of story. But then you look at the quantum bit, the qubit, and whoa, that's something else entirely. It's less like a switch and more, like a spinning coin. Because of this wild property called superposition, it exists as a combination of both 0 and 1, all at the same time. So this whole superposition thing, what even is that? Well, it's a core concept straight out of quantum mechanics. It's what allows a qubit to exist in this kind of probabilistic haze of both states at once. It's this ability to hold a whole spectrum of values that lets a quantum computer explore so many possibilities at once. It's only when you actually look at it, when you measure it, that it collapses and finally picks a side, becoming a definite 0 or 1. And believe it or not, it gets even weirder. Qubits can also be entangled. Now, what does that mean? It means two or more qubits can become linked in this spooky way where their fates are totally intertwined. If you measure one, you instantly, and I mean instantly, know the state of the other one, no matter how far apart they are. This creates these incredibly complex correlations between qubits that are just built in. A classical computer would have to painstakingly create these relationships one by one, but for a quantum system, it's an intrinsic interconnected property of the whole shebang. So this table here really brings it all home. See, classical computing is deterministic. Put in the same input, you get the exact same output every single time. It's predictable. Quantum computing, on the other hand, is probabilistic. It's all about exploring possibilities. And those correlations we talked about, classical has to explicitly create them. For quantum, they're just there, an intrinsic property, thanks to entanglement. Okay, so we've established their building blocks are totally different. But how does that actually change how they think or, how they go about solving a problem? Well, a classical computer is an absolute master of process. It runs a simple but lightning-fast cycle over and over again. Fetch an instruction, decode what it means, and then execute it. And it does this billions of times per second with incredible precision, just following a strict step-by-step path. Now, a quantum computer, it works in a completely different way. It doesn't just follow one path. It explores this massive, massive landscape of potential solutions all at the same time. It uses what are called quantum gates, which are basically operations that rotate and shift the qubit state to manipulate all those probabilities. The whole goal of a quantum algorithm is to choreograph these operations just right so that the probabilities of all the wrong answers cancel each other out, while the probability of the right answer gets amplified, making it pop out when you finally take that measurement. So you can see how this fundamental difference in thinking means each machine has its own unique set of strengths and weaknesses, right? It's like you wouldn't use a hammer to turn a screw, and you're probably not going to use a quantum computer to check your email. So where does a quantum computer really shine? Well, think about something like simulating a new molecule for drug discovery. Nature, at its core, is fundamentally quantum. So trying to model it perfectly is this problem of exponential complexity for a classical computer. It just can't keep up. It has to take shortcuts and approximate. But a quantum computer, it can model it directly, qubit for qubit, atom for atom. This could literally revolutionize medicine and materials science. And hey, this isn't just some far-off theory. In a recent simulation for a medical device, a quantum computer actually achieved a 12% performance gain over a classical supercomputer. Now, this was one of the very first documented cases of a practical, if still pretty narrow, quantum advantage. But let's be real. For the huge, overwhelming majority of tasks we all do every single day, classical computers are still the undisputed kings. Their deterministic precision, that's their superpower. Every time you open an app, send an email, or play a game, you're relying on that almost perfect reliability. And this chart, wow, it just brilliantly illustrates that reliability gap. A modern classical processor might make, one error in 100 million billion operations. It's almost perfect. Meanwhile, current quantum computers are in what we call the NISQ era. That stands for Noisy Intermediate Scale Quantum. And because qubits are so incredibly sensitive to everything, heat, vibrations, radiation, you name it, they make an error in about every 1,000 operations. I mean, that is a staggering difference, and it is the single biggest challenge for the folks building quantum hardware right now. This timeline really helps put things in perspective. For stuff like quantum simulation using algorithms like VQE, or for those super complex optimization problems using QAOA, we're probably looking at 5 to 10 years before they're commercially viable. And for the big one, the one everyone talks about, breaking encryption with Shor's algorithm, well, that's going to require a level of error-corrected fault-tolerant hardware that is likely more than 15 years away. So we've got a ways to go. So if we just throw out this whole idea of replacement, what does the future actually look like? Well, the answer isn't competition, it's collaboration. And I absolutely love this analogy because it just perfectly captures the reality of the situation. It's so good. Asking if quantum will replace classical is like asking if submarines will replace airplanes. You use the right tool for the job. They're both incredibly advanced vehicles, sure, but they operate in completely different environments. You're not going to use an airplane to explore the ocean floor, and you're definitely not going to use a submarine to fly across the country. And really, this is where the experts have landed. The consensus is that the future is hybrid. Your main processor, it's still going to be a classical CPU, but for a very specific, incredibly difficult part of a problem, the part that requires exploring that vast possibility space, it'll hand that task off to a specialized quantum processing unit, or a QPU. It's a lot like how your computer offloads graphics-heavy tasks to a GPU today. So when you boil it all down, this isn't about one machine beating another. It's about a fundamentally new kind of tool joining our computational toolkit. And the real question, the one that gets me really excited, is this. By combining the precise, deterministic power of classical computing with the mind-bending, probabilistic exploration of quantum computing, what problems, once thought totally unsolvable, will we finally be able to conquer?